Hello, everyone. In section 6.5, we actually take a look at some application problems that kind of focus on what I'm first going to introduce to you. So we're looking at exponential growth and decay. We're also going to look at investment problems when interest is compounded at different times throughout the year or even continuously. So all of these focus on this idea that we're going to first take a look at. So we're going to go ahead and let y of t be the value of a quantity y at time t, and suppose that the change in y, so the rate of change of y, dy with respect to t, so dy over dt, or the derivative of y, is going to equal ky, where k is a constant. This rate is growth if k is greater than 0. And this is decay if k is less than 0. So in order to come up with a formula that I'm sure you guys have seen throughout other math courses, but this kind of tells us where this formula comes from. And there's a variety of versions of this formula. But we're going to solve this, what we call a separable differential equation. Just abbreviating here. Solve the separable differential equation. So we're going to start with dy over dt is equal to ky. We're going to separate our variables, so I want to get all the y's to one side and everything else to the other. So we'll just say dy over y is going to equal k dt, and then we'll take the integral of each side. We could write this as 1 over y dy is equal to the integral of k dt. So think of the antiderivative of 1 over y. That's going to turn into the natural log of y. Now we're just going to keep y as positive, so we're not going to get into absolute values here. But this will be the natural log of y, technically plus a constant, but we're just going to get all of our constants to one side. So then the antiderivative of a constant is going to be k times t, and then we'll put our plus c over here. So we could technically have a plus c1 here, and then we just bring it all over to one side. So now what we're going to do is we want to solve this for y. So I'm going to use a base of e. So we'll have e to the natural log of y is going to equal e to the kt plus c. All of that's the exponent. So e to the natural log of y, we saw this in the last couple sections, that's just going to cancel out because e and natural log are inverses, so we're just going to have y. Now we're going to use a little exponent manipulation here, laws of exponents. So I'm going to separate this as e to the kt times e to the c. Because if I were to give this to you, we're multiplying powers with the same base, so we state our base once and add the exponents. Well, e to the c is going to be the initial amount. So we could also just call this y of 0. So now this becomes y is going to equal, we could say y of t is going to equal y of 0, the initial amount, times e to the kt. So this is our equation. Some other versions can be our final amount is equal to our initial amount times e to the rt, where, again, a naught here, or a sub 0, is going to be our initial amount, and then it's e to the rt, or you may have seen a is equal to p. P is our principal amount, our initial amount, times e to the rt. So these are all different versions of the same. But what it's really showing us here is this is our final amount, no matter what notation we're using. This right here is our initial amount. Again, E shows up just naturally, and then it's raised to some rate times time here. So we're going to use several different versions of this. All right, in our first example, we'll start with, say, a culture starts with 5,000 bacteria. And the number doubles every 30 minutes. After how many minutes will there be 25,000 bacteria? Okay, so we're going to start with the equation that we just wrote on the last page. I'm going to go with the first version of it. So we're going to show y of some time is going to equal y of time t equals 0, so our initial amount, times e to the kt. So first we have to figure out what is k. So a lot of times that's what we don't have. So we could just start with some other time. And if we're just looking at maybe after the first 30 minutes, it's the easiest time interval to go with. So let's just let t equal 30 minutes. Then we would say y of 30, which if it just doubles every 30 minutes, after the first 30 minutes, we're going to be up to 10,000. So we could say 10,000 is going to equal 5,000 times e to the k times 30. So again, 30 is t, so we'll have 30k. Well, now we could just start to solve this. Again, we want to find k. So we could divide both sides by 5,000, so we'll just get 2 is equal to e to the 30k. What are we going to do to get rid of e? We're going to take the natural log of each side, so we'll take the natural log of 2 is equal to the natural log of e to the 30k. So we still have the natural log of 2. Over here, natural log of e to anything is just going to be to that exponent, or we could say we bring down the 30k, and then it's really times the natural log of e, and then that goes to 1. So we're going to say k is going to equal the natural log of 2 over 30. And for right now, we just want to leave this in exact form. So this is like finding the y-intercept when you have to write an equation and you're given slope and a point. And then we would just substitute this back in. So now we have a general equation where k is given here, because if not, we had two unknowns. We had a k and a t. So here we would just say y of t is equal to our initial amount of 5,000 times e to the, and it's going to look a little weird, just be careful writing it, natural log of 2 over 30 times t. So that's our equation where we can figure anything out now. So now we need to know the time that there's going to be 25,000 bacteria. So now our final amount is going to be the 25,000 is going to equal the 5,000 times e to the natural log of 2 over 30 times t. So now we can solve this for t. So dividing 25,000 by 5,000 gives us 5 is equal to e raised to the natural log of 2 over 30t. Now we're going to take the natural log of both sides. So now we have the natural log of 5. Again, natural log and e cancel each other out, so we're looking at natural log of 2 over 30 times t. So we're going to go ahead and multiply by the reciprocal, or we can divide by this. I'm going to show t is going to equal the natural log of 5 times 30, so we can put 30 out in front, over the natural log of 2. Now you're definitely going to need calculators for this. So this is the exact answer, and then that's going to be how many minutes. But we really want to know what that is. So go ahead, carefully type this into the calculator. So this is the exact. And we could just round it 2 decimal places. So we're going to say t is approximately, that's the symbol I use for approximate, about 69.66. I said it, I didn't write it. 69.66 minutes. All right, there's our first example. Let's try another one. Okay, so we're going to work with rhodium-221. And this has a half-life of 30 seconds. Question is, how long will it take for 25% of the sample to decay? Now, with these types of questions, you have to be careful because what we really want to set it equal to is the amount after so long. So if 25% is gone, that really means 75% remains. Now, if this said for 25% of it to remain, then we would work with the 25%. So we're looking at if 25% is gone, that means 75% remains. And we're going to be working with the 75% in this case. All right, so we're going to start with that same formula, that y of t is going to equal our initial amount times e to the kt. Now in this case, we're not given an initial amount, so we could just make anything up. We could just say our initial amount is 1. So let's say, again, after 30 seconds, when t is equal to 30 seconds, we want to find k again. So let's say our initial amount was just 1. Then half of that would just be 1/2. And then that would be times e to the 30k. So really, we don't even need that 1 here. We would just say 1/2 is equal to e to the 30k. Again, we'll take the natural log of both sides. So this becomes a natural log of 1/2 is equal to 30k. And then k is equal to the natural log of 1/2 divided by 30. So now, just like the last problem, we could write out our equation that y of t is equal to y of 0 times e to the natural log of 1/2 over 30 times t. All right, so now we'll substitute in the 75% here. So we could just say, we could do 3/4, we could do 0.75. And then that's just going to equal 1, which we don't have to write. So e to the natural log of 1/2 over 30 times t. So the same process here. We'll take the natural log of both sides. So again, we get the natural log of 0.75 is going to equal just the natural log of 1/2 over 30 times t. So just like the last one, t is going to equal, multiply both sides by 30. So we'll get 30 times the natural log of 0.75 over the natural log of 1/2. Now again, this is in seconds. So carefully type that into your calculator to get an approximation. And we should be getting about 12.45 seconds. Okay, so we're going to shift to investing money. We always want our money to grow. So we're going to call this compounded interest. Now there's such a thing just called simple interest, and that's where you just do a calculation once. But compounded interest means you earn interest on the interest. So this is the version of the previous formula that we're going to use. We're going to say A of t, so that's our final amount, is going to equal our initial amount, and then we'll have times 1 plus r over n raised to the nt. So here, r is the interest rate. We always want to put this in as a decimal. N is going to equal the number of periods compounded per year. And T is going to be the number of years. So again, right here, this would be the initial amount. All right, so let's say we have a sum of $1,000 is invested at a rate of 8% per year. We're going to find the amount in the account after 2 years if the interest is compounded at different periods here. So we'll kind of do this in parts. So we want to find the amount in the account after 2 years if the interest is compounded. First, we'll do monthly. Now, if you want to pause the video and give this a try, use the formula here. All right, so for monthly, that means the interest is compounded once a month, so 12 times a year. So that means n is 12. And again, this is for 2 years, so t is 2. And r is going to be 0.08. So we'll say a of 2 is going to equal, our initial amount invested is 1,000 times a quantity of 1 plus r over n, so 0.08 over 12. And I'll raise that to the 12 times 2, n times t. And all you have to do is calculate that. So go ahead and you can pause the video if you wish to calculate that. So this should give us about $1,172.89. So now let's take a look when our interest is compounded daily. So in this case, once a day, that means 365 times a year. T is still 2, and R is still 0.08. So now we'll have A of 2 is going to equal 1,000 times a quantity 1 plus, still 0.08. But this is what's stopping it from getting outrageously high, even though we would like that. If our money's sitting in the bank, we would love to make as much money on it as possible. But they would divide that 0.08 by 365. And then we would have raised to the 365 times 2. So again, pause the video, go ahead and calculate that. And if you're noticing, it's not much more money. This is giving us $1,173.49. And then the third is continuously. It means just an infinite amount of time. So there's a new formula here. So I'm going to write this out, and then I'm going to show you where this formula is coming from. So continuously is A of t is going to equal our initial amount times e to the rt. Some of you may have seen this written out as, I call this the PERT formula. P, which is our initial amount, times e to the rt, so it literally spells out PERT. But back in the day, I don't know if you guys remember, there used to be a shampoo called PERT and PERT Plus, so we just always call this the PERT formula. But we could also write it out based off of what I showed you at the very beginning. So here we could just say A of 2 is going to equal our initial amount of $1,000 times e to the 0.08 times 2. So go ahead and calculate that. And again, you can see it's not much more either. So it's 1,173.51. So monthly, daily, and continuously are always going to be close together versus if we just did this quarterly or semi-annually or just once a year. But these are the formulas we're going to use. So let me show you where this formula is coming from, or this version of it as well. So we'll kind of answer the question, why that formula? So let's say for continuous, we're going to say A of t, we're going to use limits here. We're going to say it's the limit as n keeps increasing without bounds. So as n approaches infinity of this formula, A of 0 times 1 plus r over n raised to the n over t. Since A of 0 is a constant, we could just kind of pull that out in front, say it's A of 0 times the limit as n approaches infinity of this quantity 1 plus r over n. Now, I'm going to do a little manipulation here. I'm going to say this is n over r and then r times t up here, because this would still give us n times t. I'm just kind of dividing n by r, then I'm multiplying r by t, and you're going to see why in a second. I still have my initial amount. Then we're going to say times the limit as m goes to infinity. So what I'm doing here, I'm going to say, let's let m equal n over r. So I'm going to change this a little bit. So this is going to become the limit as m goes to infinity of 1 plus, now n over r is the reciprocal of r over n. So if m is equal to n over r, 1 over m is equal to r over n. Raise that to the mth power, because that's n over r. And then raise that to the r times t. Now the reason I did this, we're going to go back to a previous section. From section 6.2, I introduced e. One way to write e was the limit as n goes to infinity of 1 plus 1 over n to the nth power. That was approximately that 2.7 number. Well, if you look closely at everything that's here, that looks like this part. This is the limit as something is going to infinity, and then it's 1 plus 1 over m, so the m matches this m, which matches that m, and that's e. So then this becomes our initial amount times e to the rt. Nice little proof there. All right, one more type of an example. We're going to bring in some physics here. It's Newton's law of cooling. So we're going to go back to a differential equation here. We're going to say d of t, so capital T over d of lowercase t. So the capital T is going to be the temperature, and then lowercase t is time. So this is going to equal K times T minus T sub S, where K is a constant and T sub S is the temperature of the surroundings of the object. So in our fourth and last example for this section, we're going to answer this question. Let's say we have a bottle of pop at room temperature. (72°F) is placed in a fridge where the temperature is 44°F. After 30 minutes, the pop cooled to 61°F. All right, we're going to be asked to find an expression for the temperature of the pop after T minutes. Okay, so we're going to go ahead and start with the change in temperature, or the change in time, is equal to K times the quantity T minus T sub S. So the temperature of the surroundings, well, the pop is now in the fridge, so its surroundings is going to be 44 degrees. And again, we have a separable differential equation. So let's go ahead and separate this here. So we'll have dt over T minus 44 is going to equal K times dt. And we'll go ahead and take the integral of each side. So I'm going to write this as 1 over T minus 44 times dt is equal to the integral of K dt. All right, so again, 1 over something here, and it's nice. We don't really have to use substitution here. This is just going to be the natural log of the quantity T minus 44. Because if we were to take this derivative, we get 1 over T minus 44, but then times 1. So that's going to equal, again, K is a constant, so we'll get KT plus C. We're going to use a base of E on both sides, so we'll have E to the natural log of quantity T minus 44 is going to equal E to the KT plus C. So this is, again, very similar to what we did at the very beginning. E to the natural log is going to cancel out, so we get T minus 44. We'll separate this using exponential laws of exponents. So we'll get E to the KT times E to the C. Again, E to the C is the initial amount. So we're going to have T, so the temperature at time T is going to equal 44 plus E to the KT times E to the C. Or really, we could write this as the temperature at time T is going to equal, we could put T sub 0 here. Times E to the KT plus 44. So now we know at time 0 that the pop has a temperature reading of 72 room temp at 72 degrees. So we could use that now to help us find K, or this initial amount. So we're going to have T of 0. And actually, I'm going to go back just because I'm using this T of 0 here. I want to go ahead and just call this the E to the C so that doesn't get too confusing here. So we'll just still call this E to the C. So then this will become E to the C times E to the K times 0, and then plus 44. So our initial temp over here, T of time 0 rather, is going to be 72. This will just give me E to the C plus 44. So E to the C is going to equal 28. So now as we continue, we could say our temperature at time T is going to become 44 plus 28 times E to the KT. And now we want to figure out what K is. So we go back up to the statement that after 30 minutes, the pop cooled to 61 degrees Fahrenheit. So again, we're doing all of this. So this would be our initial time going into the fridge. And then we have 28 degrees here for our initial temp. So looking at this now, we can say after 30 seconds, I'm sorry, 30 minutes rather. So T is going to equal 30 minutes. So that would be 61 is going to equal 44. So we want to find K. So plus 28 times E to the 30K. 61 minus 44 will give us 17 equals 28 times E to the 30K. Divide by 28. We could just leave that as 17/28. We don't want to do any rounding until the very end. So that's going to equal E to the 30K. What are we going to do next? Take the natural log of both sides. So the natural log of 17/28 is going to equal the natural log of E to the 30K, which just becomes 30K on this side. So K is going to equal the natural log of 17/30 over 30. So really, again, we're not really finding a specific answer. We want to just write the equation, an expression for the temperature of the pop after T minutes of being in the fridge. So therefore, our final answer is the temperature at time T is going to equal this 44 plus 28 times E to the natural log of 17/30 divided by 30 times T. All right, so at least for today, these were all the examples I'm going over. A lot of times I'm going to tell you guys too to bring your devices to class. That way you can get started on the homework assignment. But because we're going to have a quiz coming up, if quite possibly next week, I'll also be going over some review problems, and I'm going to do this separate of this video. So again, this was just focusing on section 6.5. Let me know if you have any questions.